Welcome to Ellipse video number 9. And for this video, I'm actually in our class GeoGebra account. So if you wanted to go to GeoGebra, you can just Google, it's all free, the Mrs. Bailey's Pre-Calculus Accelerated Honors book. If you click inside of there, you're gonna see that I am in the tab labeled Ellipse, and you can kind of go back later and check this out and kind of play around with it. But this is where I am for this video. So I encourage you to go back and try that and click on it and play around with it. But basically I want to give you sort of a formal mathematical definition of an ellipse. Okay, so we are now aware of what a focal point is, right? The focal points are located equal distances from the center of the ellipse. This particular ellipse is a horizontal ellipse. It looks like the major axis is longer than the minor axis, or I'm sorry, the major axis is the x-axis, right? Because the major axis looks like it's a little over 16 and the minor axis looks like it's less than that. So if I have one focal point and another focal point, the definition of the ellipse says that if I pick a point on the ellipse, point P, and if you look at these green lines, so the distance from P to F plus the distance P to F prime, this distance will stay constant as I go around the ellipse. So up here, you'll see there's a calculation, right? Distance is absolute value. So the length of PF plus the length of PF prime is going to remain constant at 16.6. And the computer is just calculating that distance based on the distance formula. Okay, so watch what happens. And again, you'll get to play around with this when you go into GeoGebra, okay? So I'm gonna click on this point. Now watch the 16.6. You can see the individual segment lengths differ, but the total of 16.6 is staying exactly the same. And that's happening as I go all around the ellipse. Okay, the distance of the sum of the distance between the point on the ellipse and the focal points is exactly the same, okay, no matter where I go, okay? It's pretty cool. That's one of the mathematical properties of the ellipse. And you'll notice I can change the major axis, right? I can change A to be maybe, I don't know, I can change it to be anything I want. This is actually kind of cool. So let me just change it a little bit here. All right, let's do that. And now the distance is 13.8. You can see that regardless, those two segments added together remain exactly the same. So if I were in class with you, I would actually do the formal mathematical derivation of the equation for the ellipse based on this property. If you are curious about the math behind this, I want to encourage you to open up my 9.2 ellipse notes. I'm just going to kind of show you. It's going to be, I think, on page number 5. I kind of go through the mathematical derivation of how we get the ellipse formula. I'll leave you to read through that if you're interested. But basically, it's going to use, you guessed it, the distance formula. If you don't go through the technical derivation, you can just understand this demonstration. I think this is priceless for understanding the definition of an ellipse. And if you just watched the video on Edpuzzle on the Whispering Gallery, which if you haven't done yet, I would strongly encourage you to do, think about where those two people were, right? The one guy playing the guitar in Grand Central Station was standing at one focal point, and the sound was basically taking this path. It was going up, bouncing off the top of the ellipse, and back to the other person standing at the other focal point. So this is how Whispering Galleries work, taking advantage of these focal point properties, okay? So I hope that was helpful. Again, I encourage you when you're finished this video to go into GeoGebra and play around with this particular diagram.